everyone, my name is Alina Dowson. There are many genetic disorders that are passed down through families over generations. Homocystinuria is one of those disorders. So what exactly is homocystinuria? It is an amino acid disorder specifically having to do with the amino acid methionine. In a normal individual, methionine is normally converted into homocysteine, and the final product we want from that conversion is just plain old cysteine, which is a different amino acid that has many roles in the body. To get to that end product, though, of cysteine, we need the enzyme cystathionine beta synthase. So people with homocystinuria cannot zyme, which means that they cannot metabolize methionine. So like I said there, it's caused by a deficiency of the CBS enzyme. It affects ocular, nervous, skeletal, and the vascular systems, and obviously because it affects so many parts of the body, there is a wide array of symptoms. So looking at numbers that are associated with homocystinuria, it has a global incidence of, and then I have listed here several countries, so Ireland, Germany, Norway, and Qatar. They have a higher incidence of this disorder, and Qatar being the most prevalent, it's 1 in 1,800. So one of the reasons for this can go back to consanguinity, which is when people are related and they have offspring together. So more people that are clustered together that are carriers for this disorder, when they have offspring, they obviously have a higher instance of this disorder. So looking at the symptoms, we have Island's dislocation, nearsightedness. The person can have developmental issues, learning disabilities, abnormal blood clotting. There can be osteoporosis, which is just the weakening of the bones. They have long arms and limbs, and sometimes scoliosis, which is curvature of the spine. So with diagnosing homocystinuria, early detection is imperative. As you saw on the earlier slides with the symptoms, if you detect this earlier, there are interventions that can be done that will help the individual that has the disorder not be as affected, so they wouldn't have as many symptoms. So it is part of the uniform screening panel that children are all tested right after birth, so usually it's 1 to 2 days old, and they get a heel prick, and they give a blood sample. And the children are tested regardless of their insurance status. So the treatments for homocystinuria, normally half of individuals respond to vitamin B6, and if they do, they have to continue on vitamin B6, vitamin B12, and vitamin B9 vitamins for the remainder of their life. The other half has to maintain a low methionine diet, which is typically like a vegan diet, so it's high in fruits and veggies and nuts and beans. So looking at the genetics of homocystinuria, there are several different genes that have mutations that can cause the disorder, but the most common is the CBS gene, which I described earlier, the cystathionine beta synthase. The chromosome location, looking at this, it's 21q22.3. So 21 means it's on chromosome 21, and Q means that it is on the long arm of the chromosome, and 22.3 just defines which bands and subbands it's located at. So the mode of inheritance is autosomal recessive, which means that both mother and father have to carry the trait for their child to be affected. So talking about mutations, mutations are simply just alterations of a nucleotide sequence. This one is specifically caused by a missense mutation. So it causes unstable misfolded proteins, and then the protein degrades. And the thing about this is proteins have to maintain a specific structure to work properly in the body. So obviously if you have the degradation of the protein, it's going to break down in the body, and that's why the patient has the symptoms that it does. Alrighty, so I already said that the disorder is caused by an autosomal recessive trait. That just means that both parents have to carry the recessive trait. So if you can see here, get a little laser pointer, this here, the capital A would be the dominant trait, the lowercase a would be recessive, so this is the mother's traits here, and then over on this side you have the father's traits. It's the dominant as well as the recessive. So when you look at the Punnett square, you can see that there is the probability, and sorry about that, I know you can't see that part. Okay, so the probability here of two parents that are carriers having an offspring with the disorder is 1 in 4. And the probability that they give birth to carriers is 2 in 4. And then they have a 1 in 4 chance of having a child that's not affected at all. Alrighty, so then looking at the pedigree here. So with a pedigree, you can kind of see how disorders are passed down through generations and families. So I'll get my pointer back here. So if you look at the key over here to the left, the squares represent males, the circles represent females, and if there is a square or a circle with the little green, the right bottom corner is green, then that means that the individual is affected, so they have the disorder. If there is a pink circle in either of the square or the circle, it means that they are a carrier. And then obviously if there's nothing in the box or the circle, it means that they're unaffected. So if you look here, under each male or female, you have the name, the age, as well as their genotype. So this shows you the dominant and the recessive trait, or in the case of this person, Jasper, they have both dominant traits. Okay, so if we look at the top here, looks like it started with a gentleman that was a carrier. He had offspring with a woman that was unaffected, and they gave birth to a son that was a carrier. So the son then had offspring with another carrier here, so they had an affected individual. So you can see how when two carriers come together, they have the probability of having a child with the disorder, and if that person that's is affected has a child with someone who is a carrier, you have a higher instance here of them having a child with the disorder. So this is just showing you these two people are carriers. They have a child here that has the disorder, but they have offspring with a woman that is unaffected. So then they give birth to a couple carriers. So this just basically shows you, as I said, how it's passed down from one generation to another. Okay, and then if we look into the genetic testing for this disorder, so like I said, newborns are screened for this disorder, and it's usually right after birth they test the methionine levels. But for people who want to find out, if they're a carrier of this disorder, or they have family members that have it and they just want to see, what their chances are if they have a child, you can go through these companies. There's actually 2 examples here. It's Blueprint Genetics and Prevention Genetics. The price varies, so it's from $14.50, and then the second one here is $890. This is something that should definitely be pursued with a healthcare professional. Any kind of genetic testing, you would want to work with someone that is used to seeing the material and understands it, so that it can help you better understand it. So that's all. Got my references here, and that's it. Feel free to leave any questions if you have any. Thank you.